So welcome to a new video on our damage mechanism series. In this video we are going to talk about wet H2S damage, which covers all other types of hydrogen damage such as hydrogen blistering, hydrogen induced cracking, stress induced hydrogen induced cracking and stress corrosion cracking for sulfur. This kind of damage mechanism is mostly subjected to pressure vessels. This type of damage is not very much subjected to piping systems, but still it can happen, but in most cases it is going to be subjected to pressure vessels. Again, I have said this before as well when we are talking about chloride stress corrosion cracking, that a stress corrosion cracking that happens with chlorine is considered to be chloride stress corrosion cracking. If it's happened due to ammonia, then it is ammonia stress corrosion cracking. If it happens due to sulfur, then it's sulfur stress corrosion cracking. Now, the next thing about hydrogen induced damage is that hydrogen induced damage is generally going to be prevented by post-well heat treatment if you're doing it in carbon steel. So in carbon steel, post-well heat treatment, one of the main reasons that you do post-well heat treatment is to reduce hydrogen induced damage, so that whatever the entrapped hydrogen inside the base metal is there, that will be removed during post-well heat treatment. If it's not done, then when the metal temperature goes below 200 degrees Celsius, then you will have hydrogen induced cracking, the cracking that will develop because of the hydrogen presence, and that is going to be a detrimental factor. This is generally going to be associated in the heat affected zones. Secondly, blistering. Blistering is basically a bubble formation inside the material. You will understand it very easily when I show you the pictures, but that is also hydrogen induced damage. This happens due to hydrogen presence. So description of damage. This section describes 4 types of damage that results in blistering and or cracking of carbon steel, one of which also affects low alloy steels and some other high strength or hardenable materials in wet H2S environments. Hydrogen blistering. So hydrogen blisters form bulges primarily on the ID surface of a pressure vessel. So you will see bulges, you will see a bubble formation on the ID side of the pressure vessel. Hydrogen blistering is rare in seamless pipe, but it can occur in seam welded pipes. Blisters are caused by hydrogen atoms that form on the surface of the steel as a result of corrosion reactions. Sulfur acts as a recombination poison, delaying the combining of hydrogen atom into hydrogen gas, allowing the hydrogen atoms to linger on the steel surface. Small hydrogen atoms can then readily diffuse inside the material. The hydrogen atom diffusing in the steel can collect at a discontinuity such as inclusion or lamination, where they combine to form hydrogen gas because there is no recombination poison within the steels to inhibit this reaction. So basically you'll see blisters. Next is hydrogen induced cracking. Hydrogen induced cracking results from the same cause as blistering, basically hydrogen entrapment. That is the form of hydrogen atom diffusing into the steel as a result of corrosion. However, in this case, when the hydrogen atom diffuses into the steel, rather than forming a blister, internal separation parallel to the surface of the steel is a result. That means you'll see a cracking. Again, it is the pressure buildup resulting from the hydrogen atoms combining to form an H2 gas or hydrogen gas that can cause the internal separation within the wall of the vessel. The separations are initially microscopic in size but can connect together to form a macroscopic size cracks. Interconnecting cracks between hydrogen induced cracking separations on different planes have a stair-type appearance, and so hydrogen induced cracking is sometimes referred to as step-type cracking. Again, hydrogen induced cracking, if it's in a high stress environment, then it will be considered to be SOIC or stress oriented stress corrosion hydrogen induced cracking. So SOIC is stress oriented hydrogen induced cracking, again a form of hydrogen cracking. So SOIHIC results from the array of hydrogen induced cracking stacked on top of each other. When acted upon by a high stress level, the stacked hydrogen induced cracking will connect and create a through wall thickness crack that is perpendicular to the surface. HOSIC most oftenly occurs in the base metal adjacent to the weld heat affected zone, the residual stresses from the welding being the most common driver of SOHIC, and can initiate from the stacked HIC alone, from sulfide stress corrosion cracks or other form of crack like defects or stress concentrations. Sulfide stress corrosion cracking, now this generally will happen because of sulfur that is in presence with some stress components applied to the part. Sulfide stress corrosion cracking is a cracking of a susceptible material under a combined action of tensile stress and corrosion in the presence of water and H2S. Stress corrosion cracking is a form of HE cracking resulting from absorption of the atomic hydrogen that is produced on the metal surface by corrosion products. Stress corrosion cracking occur in high strength, high hardness steels, but can also initiate in the highly localized zone of the high hardness in weld metal and heat affected zones. So generally to reduce all of these things, we'll generally do post-weld heat treatment on carbon steels. So post-weld heat treatment is beneficial in reducing the high hardness and residual stresses that render the steel susceptible to stress corrosion cracking. And it is essential when welding a hardenable low alloy steel including chromium moly steels as well as martensitic stainless steel. Some carbon steel contain REs that form hard areas in the heat affected zone that will not temper at normal stress relieving temperatures, using a preheat to minimize this hardness problems. Affected materials: carbon steel in case of stress corrosion cracking, low alloy steels and martensite stainless steel. Critical factors: a liquid water phase containing H2S, that is SAR environment, must be present and must be in contact with the steel in order for wet H2S damage to occur. Equipment that is highly susceptible to stress corrosion cracking can fail even during the short SW extrusions, SAR water extrusions, such as might be encountered during the equipment shutdowns. Beyond this, the critical factors that affect and differentiate the various forms of wet H2S damage are environmental conditions and material properties and tensile stress levels. All of these damage mechanisms are related to absorption and permeation of the hydrogen inside steel. Secondly is H2S level, then pH level of the sulfuric acid solution or sulfur solution. So hydrogen permeation and diffusion rates in steel have been found to be minimal at a pH 7 and increase at both higher and lower pH. pH 7 is basically water, okay, neutral. Anything that is neutral is pH 7. Temperature: blistering, hydrogen induced cracking, stress oriented hydrogen induced cracking have been found to occur at ambient temperatures and 300 degrees Fahrenheit or higher. Stress corrosion cracking potential is greatest at about 20 degrees Celsius or 70 degrees Fahrenheit and decreases with increasing or decreasing the temperature. This is likely related to the rate of hydrogen diffusion and its behavior in the steel at different temperatures. Stress corrosion cracking is generally a concern below 95 degrees Celsius. Hardness. Hardness is primarily an issue with stress corrosion cracking. Blistering, hydrogen induced cracking or stress oriented hydrogen induced cracking damage is not related to steel hardness. Typically, carbon steel used in refinery application are not expected to be susceptible to stress corrosion cracking because their strength and hardness is sufficiently low. Generally, that is one of the reasons also to do post-weld heat treatment, because if you do a post-weld heat treatment, then generally the hardness levels would go down. The welds in carbon steel should be controlled to produce a weld hardness lower than 200 HB or brittle hardness value, and will typically achieve this without any special precautions. Carbon steel welds are not susceptible to stress corrosion cracking unless the localized zones of hardness about 237 brittle hardness value or brittle hardness number are present. Tensile stress level: blistering and hydrogen induced damage develop without the application of the residual stress. The post-weld heat treatment will not prevent them from occurring. The tensile stress is needed to cause stress oriented hydrogen induced cracking, typically comes from the weld residual stresses, which in absence of thermal relief stress relief are typically very high, that is approaching the yield strength. High local stresses or notch like discontinuity such as shallow sulfide stress cracks can serve as initiation sites for stress oriented hydrogen induced cracking. Post-weld heat treatment is somewhat effective in preventing or reducing the stress oriented hydrogen induced cracking damage. Affected equipment: blistering, hydrogen induced cracking, stress oriented hydrogen induced cracking and stress corrosion cracking. Damage can occur throughout the refinery wherever there is a wet H2S environment present. So almost everywhere it can happen, but generally more subjected towards pressure vessels. Appearance: all four forms of wet H2S damage are best illustrated through the photos in below. So we'll talk about these photos. Hydrogen blisters appear as bulges, most often on the ID surface of the steel, but can be found anywhere in the shell plate or head of a pressure vessel. Blisters can be typically found in rare occasion in seamless pipes. However, large diameter seam welded pipe, which is typically made from a plate similar to that of a pressure vessel, will have susceptibility comparable to pressure vessels. Blisters has even been seen in the middle of the weld, but it is very rare. Late stage hydrogen induced cracking or stress oriented hydrogen induced cracking will create surface breaking cracks. Pressure containing equipment, stress oriented hydrogen induced cracking and stress corrosion cracking damage are more often associated with the weldments. Blisters and hydrogen induced cracking typically are not associated with the welds, but rather occur within and sometimes throughout the shell plate or a course. However, they can grow towards and intersect the weld, which increases the likelihood of stress oriented hydrogen induced cracking in the heat affected zone and can develop a through wall crack. Prevention and mitigation: you can have effective barriers so that your surface can be separated from the H2S environment. This will prevent blistering, hydrogen induced cracking, and stress oriented hydrogen induced cracking. Process change that affect the pH level of the water phase or ammonia or cyanide concentration can help reduce hydrogen blistering. Hydrogen induced cracking resistant steel can be used to minimize the susceptibility to blistering and hydrogen induced damage. Post-well heat treatment will minimize the susceptibility to stress oriented hydrogen induced cracking. Post-well heat treatment will not prevent hydrogen blistering or hydrogen induced cracking because they are not initiated by the stress but usually occur away from and not associated with the weldments. Surface stress corrosion cracking is in welds are typically be prevented by limiting the hardness of the carbon steel value and the heat affected zone to about 200 VHN maximum. The similar but slightly higher maximum hardness limits are normally placed on chromium moly steels, for which high hardness is prevented by using preheat, post-well heat treatment and a welding procedure control. Inspection and monitoring: the process condition should be monitored and evaluated by process engineers and corrosion or material specialists to identify the equipment where the conditions are most likely to promote wet H2S damage. Blisters are normally identified by VT. Inspection of stress-oriented hydrogen-induced cracking focuses on weld seams and nozzles. Cracks from stress-induced hydrogen-induced cracking or surface-breaking hydrogen-induced cracking may be seen visually. However, to enable crack detection at early stage, wet fluorescent magnetic particle testing, eddy current testing, or alternating current field measurements technique may be used. Surface preparation by grit blasting or high water pressure water blasting, flapper wheel cleaning, and other methods are usually required for wet fluorescent magnetic particle testing, but not for ACFM or ECT. PT cannot find tight cracks, so PT would not be a reliable technique for identifying stress-oriented hydrogen-induced cracking or hydrogen-induced cracking. Angle beam inspection, angle beam UT can also be helping you in doing this, or you can also use post-well heat treatment where you are suspecting that the crack that is being developed is generally subsurface or internal to the surface, or if you want to size the crack internal to the surface, then UT and post-well PAUT is going to be the better options. Internal HIC can appear to be deep, clearly defined, individual sharp cornered pits when using straight beam UT for thickness measurements on the shells or heads. Acoustic emission testing can be used to locate crack and monitor crack growth. If cracking or a failure due to sulfur stress corrosion cracking is not visually apparent, the cracks are normally found by using MT if they are surface breaking and there is an access to the surface, or angle beam UT, PAUT or shear wave UT if they are surface breaking or inaccessible internal or at the inaccessible internal surface. There are some related mechanisms, that is hydrogen embrittlement, hydrogen stress corrosion cracking, DMW, amine cracking, carbonate cracking can also occur in a wet H2S environment and may have similar appearance. So in this case, these are hydrogen blistering. You see a bubble formation outside the material. So this is a blister that is forming. Blistering is not associated with the weld only. So this is a blister. So this is the blistering on the surface that you can see. So this, every bubble is hydrogen blister. This is a hydrogen induced cracking. A step-like occurrence is being formed. Again, hydrogen induced cracking, a macro image. Again, a step-like appearance for hydrogen induced cracking. Again, the same thing, in the heat affected zone you are able to see these kinds of cracks. These cracks are going to be hydrogen induced cracking. Now if the weld is not post weld heat treated, then it can also be called as a stress induced hydrogen stress oriented hydrogen induced cracking. So again, the same thing on the heat affected zone you will be able to see adjacent to the weldment. Again, the same thing for fillet welds. Stress oriented hydrogen induced cracking is apparent. Here you can see these kinds of cracks. Wet fluorescent magnetic particle testing has been done on this. Again, same thing, transverse crackings can be seen. Sulfur stress corrosion cracking in a hard heat affected zone is also due to hydrogen or H2S damage. They will have crack-like appearance. And that's it. So this is all for this video on the damage mechanism series. In the next video, we'll be talking about some other damage mechanism that are subjected to refinery operations for fixed equipment. Thank you, and that's it for this video.